Hey everyone, in this video we're going to go over the concept of absolute extrema, which is when we have an absolute max and a maximum minimum value of a function. And we'll also go over a relative extrema, which are when we have local maxes and mins. So I'll go over what all of that means. So let's start with this problem. Let f of x be this function, this polynomial, and we want to determine where the function has horizontal tangent lines. So horizontal tangent lines, think about what does that mean about the slope of a line. When it's horizontal, we know that the slope is 0. So that means that we want the derivative of our function to be 0 to figure out where the line is horizontal. The tangent line is horizontal for this particular function. So we're going to take our derivative. So f prime of x will be of this function. So the derivative of 2x cubed is 6x squared. Minus the derivative of 3x squared is 6x and minus 36. And now we want to know for what values of x is the slope going to be 0. And so here notice that we can factor out a 6. So we'll be left with just x squared minus x minus 6 equals 0. And that looks like it factors into x minus 3 and x plus 2. So that means that this function has two horizontal tangent lines. We have one when x minus 3 is 0, which means that when x is 3. And we have another one when x plus 2 is 0, which means when x is negative 2. So at those two values, our function up here is going to have horizontal tangent lines. So let's take a look at the graph of this function real quick. So here's our graph for f of x. So this is our original function, right? F of x is 2x cubed minus 3x squared minus 36. And so we can see that this is going to have horizontal tangent lines when x is equal to 3. So I'm assume that that's this value. So you're going to have a horizontal tangent line here. The slope is 0. And you have another horizontal tangent line up here, which is when x is negative 2. The slope is 0. So these values, x equals negative 2 and x equals 3, are also called critical numbers. So critical numbers are essentially where we have the slope, the derivative is 0, or also where the derivative is undefined. So because the derivative, the slope of the tangent line is 0 here, these are critical numbers. And the reason that these are important is because they also help us decide when a function is increasing and decreasing based on their slope. So this is where the slope is 0, but notice what happens before that value. So before x is negative 2, what is happening to the slopes here? Notice that if you draw a tangent line, the slope is going to be positive, right? This is an increasing tangent line, and all of these, in fact, are going to be positive values. So the slope here is greater than 0, which means the derivative of the function is greater than 0. And then what happens on the other side? As you go, then you hit 0, the horizontal tangent line, and then what happens to the tangent lines on the other side over here? Notice that now their slopes are negative values. So here, the slope is negative. So that means that the derivative is negative. And so when you think about the function, so when the slope is positive, what does that tell you about the y values of the function? The y values are increasing. And then when the slope is negative, the y values of the function values, right, are decreasing. So when the slope is 0 and we have increasing 0 and then decreasing, that means you have a maximum here. So at x equals negative 2, you have a maximum value. But it's not the maximum value of the function, because notice that the function keeps going on forever, right? So then this is what we call a local max. Sometimes you'll see it called as a relative max. And then here at x equals 3, you're going to have a relative min. So that is a local minimum, or also called a relative min. And so that is when you go from the function is the y values are decreasing, 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 right? They're getting smaller. And I say that as you move from left to right, you look at the y values. The y values are getting larger, so that means the function is increasing. And then the function is decreasing, the derivative is negative. And then you hit a horizontal tangent line, right? These are, in pre-calculus, in algebra, we call these peaks and valleys. So at those peaks and valleys, you have critical numbers. The slope of the tangent line is 0 there. And then notice as you move across from this slope of 0, and then you start having positive slopes again. So the function starts to increase again. And so that when you go from decreasing to increasing, that creates a local minimum. So to summarize what I just said, we can say then that a function is increasing when the derivative is positive. So let me write that down. And likewise, a function is decreasing when the derivative is less than 0. So the x values when f prime of x is equal to 0 or f prime of x is undefined are called critical numbers. So in this case, then x equals -2 and x equals 3 are critical numbers. So we can use the critical numbers to figure out when, for what intervals is a function increasing in or decreasing. Looking at the graph, we can see where the function is increasing. I can say, oh, from anything before -2 is increasing, and then anything after 3. But what if we don't have the graph of the function available to us? Then we're going to look for critical numbers, which are in this case -2 and equals 3, and then we're going to use test points to test whether the function is increasing or decreasing. So the way we're going to do that is kind of like when we did domain way back when in chapter 1. So we're going to put our critical numbers here, -2 and 3. You don't have to put 0 in there. We don't have to divide the number line evenly. Just put your critical numbers in there. And so normally what I do is I set what my derivative is doing. So this is f prime, and then I set then what f is doing. So standard f of x. So choose test points in each interval. So we have 3 intervals here. So we have the interval -infinity to -2. So pick a test point there. Then you have the interval -2 to 3. So choose a test point there. And then you have the interval 3 to infinity. And so we will choose a test point there. And what are we testing? Well, as we set up here, if a function is increasing when the derivative is positive. So if the derivative is positive, we can say the function is increasing. If the derivative is negative, we can say the function is decreasing. So we're really trying to see, when we pick a test point, we're going to choose a test point and plug it into the derivative. So let's remember, what was our derivative? F prime, after we had simplified it, we had 6 times x minus 3 and x plus 2. So that was our derivative. So when we pick a test point from here, so say between -infinity and -2, pick x equals -3, right? And then you're going to plug it into the derivative. So you're taking your test point and you plug it in the derivative. Let me rewrite this. I need more room. Okay, this is a little better. I just moved everything around. Okay, so when we x is -3, we're going to test it into the derivative. So you're going to plug it into our derivative, which is f prime equals 6 times x minus 3 and x plus 2. So when x is negative 3, you're going to have 6 times negative 3 minus 3 and then negative 3 plus 2. So you're going to have positive, negative times a negative. So you have, well, this, we can ignore the 6, that's always positive. So just look at the things in the parentheses. So I have a negative number times a negative number, which is positive. We're testing it into the derivative. So what I just found out is that when x is negative 3, and negative 3 is a representative of this interval, the derivative is positive. So that means that here the derivative is positive. What does that tell us about the function? We said if the derivative is positive, the function is increasing. And now let's look at a representative between negative 2 and 3. So for that interval, and we can be nice to ourselves and pick x equals 0 and plug it into the derivative. So it will be 0 minus 3 and 0 plus 2. So I can already see that's going to be negative times 0 plus 2 is positive, right? We care about the sign, not necessarily the value, but we want to see is the derivative positive or negative. So I just look at a negative 3. I'm going to ignore the 3 and just say that's a negative number. 0 plus 2 is 2, but that's positive. So negative times a positive is negative. So 0 is a representative of that middle interval. So the derivative is negative. What does that tell us about the function? If the derivative is negative, the function is decreasing. So f prime, positive, negative, the function is going up, going down, right? Increasing, decreasing. And then pick something, a representative on the interval 3 to infinity. So we can pick 4 or 10 or 100. So I'm just going to pick 4 and plug it in. So I'm going to have 4 minus 3 and 4 plus 2, and I can see that everything is going to be positive. Positive times positive is positive. I'm plugging it into the derivative, right? So this tells me then the derivative is positive, and therefore I know the function is increasing. So then I can say with those critical numbers, then my function f of x is increasing on what intervals? Increasing on let's see where it was positive. So minus infinity to minus 2. Ideally we would have the number line visible, so you can just look at the number line. So minus infinity to minus 2 and then 3 to infinity. So union, to put them together, 3 to infinity, and f of x is decreasing on what intervals? So it's where the derivative is negative, so it's going to be on the interval negative 2 to 3. These are always open intervals, so not including, because at those points, or those are critical numbers, the function is neither increasing nor decreasing. The slope of the tangent line there is 0, the derivative is 0, or undefined, right? That gives us the critical numbers. In this particular case, negative 2 and 3 is where the derivative is 0. So oftentimes you'll see that I'll write a little 0 here. This on the top, I'm indicating what the derivative is doing. So here the derivative is positive, the derivative is 0. The derivative is negative, the derivative is 0. The derivative is positive. When it's undefined, I'll write a little u there, because if the derivative is undefined, then that creates certain complications, right? We have to see whether that is a true max or min, or if it's an asymptote. Why is the derivative undefined? All right, let's try another example. So in this example, we want to find any critical numbers for this function. So critical numbers, again, is where the derivative is 0 or undefined. So we can say where f prime of x equals 0, or where f prime of x is undefined. So let's take the derivative. So f prime, using the general power rule, will be 2/5 x to the subtract 1. So it'll be 2/5 minus 1. So what does that give us? So that will be x to the negative 3/5. So rewrite it as a, right, we don't want to have negative exponents, so rewrite it. So this will be 2 over 5 x to the positive 3/5. And so normally you set the derivative equal to 0 to find any critical numbers, but we have a fraction. And a fraction is 0 when the numerator is 0, but this is never 0, right? So then f prime of x is never 0. So that means that f of x has no horizontal tangent lines. But what do you notice about the denominator? Right? The denominator can be 0. So that means that this is undefined at x equals 0. So let's say, but f prime of x is undefined when you have a fraction. The fraction is undefined when the denominator is 0. So this is undefined when 5x to the 3/5 equals 0, which is at x equals 0. So there are no horizontal tangent lines, but the derivative is undefined. So we do have a critical number. So f of x has a critical number of x equals 0. Right, so this is where the derivative is undefined. So what is happening at 0 then? There's no horizontal tangent line there. So what is happening with this function? And so let's take a look at the increasing and decreasing part of it. So let's set up our number line. And we only have one critical number. This is when x is 0. So we're going to be looking at f prime. And we're going to be looking at our function f as well. So at 0, when x is 0, the derivative is undefined. So that's what I mean by sometimes I'll do the little u to indicate that the derivative is undefined there. And so let's look at our intervals. So I have negative infinity to 0 and 0 to infinity. So let's pick a test point. So we want to test the derivative. And our derivative is f prime equals to 2 over 5x to the 3/5. So when x is negative, so let's say x is negative 1. Then play it in, and what do you get? So f prime is going to be 2 over 5 negative 1 to the 3/5. So is that positive or negative? Negative 1 to an odd power remains negative, so negative 1 cubed will be negative 1, and then the fifth, that means the fifth root, right? So 3/5 is this is really the fifth root of negative 1 cubed, and an odd root is also negative, so this is going to be a negative value. So the derivative is negative, which means that the function is decreasing, right? And then as we pick another test point in our next interval, so in 0 to infinity, pick x equals positive 1, then the derivative is going to be 2 over 5 and 1 to the 3/5. 1 to any power is just 1, so this is going to be positive. So the derivative here is positive, which tells us that the function is increasing. So we have a relative minimum. So this is a local min at x equals 0. And so let's take a look at the graph. So here's the graph of the original function, r x to the 2/5. So when I put that in decimals, this is the graph that I got. So notice that we can see now why the derivative is undefined at 0, right? We have a cusp at x equals 0, which means there's not a single tangent line there. You could have infinitely many tangent lines there, so that's why the derivative is undefined. But it does still give us a minimum for the function, and in fact this is because that is a local minimum based on the increasing and decreasing, but it's also an absolute minimum because it is the lowest point on the graph. So an absolute minimum is the lowest point on the graph. The lowest value of the function. And this, we can't really say that we have an absolute max because technically, right, these go on forever. So in order to have an absolute maximum, sometimes if we close it off at an interval, so I can say, what about between -2 and 2? Now this will have an absolute minimum still being 0, and we would have an absolute max at whatever those values are. So if I truncate the graph by restricting to a closed interval, now I can say that we have an absolute maximum and an absolute minimum. And that is the extreme value theorem. So in the next video, I'll talk about the extreme value theorem and absolute maxes and minimums.